Hi guys, so what we're going to do today is solve some exponential growth and decay word problems. This is going to be some common applications of log and exponential functions, and it's actually going to follow a very similar process to what we had to do for the math portion of your project. So what we're going to do here, we're going to look at an example starting with half-life. Okay, so it tells us that a certain isotope of sodium has a half-life of 15 hours. We want to determine how many hours it'll take for 40% to remain. Right, so with any half-life question or any other exponential growth or decay question, we're going to use the formula that you guys see here. And what I'm going to do is I'm just going to give you guys what those variables stand for. So y sub t is the amount that you have after whatever time t you choose. Again, very similar to what you did for the project. You had temperature t, this is the amount basically of whatever it is you're talking about. Y naught, that is your initial amount, like it usually is. R is our rate, and our rate is going to be as a decimal. So for example, if you're given the rate, let's say you were given a rate of 8%, that would go in as 0.08. These need to be as decimals. Just keep that in mind. And then t is time. It doesn't matter if your time is minutes, hours, whatever else, seconds, but your time needs to be consistent throughout the entire problem. So if you use it as hours, it's going to stay as hours. And if you guys notice, this is very similar to what you had in your project. The only difference is you had one additional variable in your project with that surrounding temperature, but after your first step, after you combined what was in the parentheses and subtracted that other number, you ended up actually with the same formula. So this process here hopefully will look similar. So what we're going to do is we're going to set this problem up using the given information. And what we have to do first, just like we had to when we had to solve for k, we need to solve for r. Now the half-life is not actually the rate. Okay, the half-life is not the rate. We use the half-life to determine the rate. So the reason I'm doing a half-life question first is because it's probably the most difficult out of these word problems because we tend to forget that. So we need to actually solve for our rate. And what I know about half-life is the amount of time it takes to decrease by half. So if I have 2 grams of something, after 15 hours I will have 1 gram because it's half of it. You can pick any values that you want as long as the one on this side is half of the other side. It's half of the initial amount. So that's my amount after time, that's my initial amount. E is E, the constant, 2.71. My R here I'm trying to solve for. And then my T, in this case, is 15 hours. So I'm going to use 15 because that's what the half-life is. Okay, so the reason I pulled these numbers, again, it took 15 hours for it to go from 2 to 1. Now I can use this process, or use this equation to solve for R. And then once I know R, then I'll figure out the rest of my information. Okay, so I need to solve for R first. And in that process, algebraically, the first thing I need to do is get E by itself. So this becomes 1/2. Once E is by itself, you can rewrite it as a natural log. So this becomes the natural log of 1/2 is equal to 15R. Get R by itself, divide by 15. And at this point, we're just using a calculator. So I'll use a calculator to evaluate this. So I have the natural log of 1/2 divided by 15. And just very similar to what we did in the project, I do need to go at least 4 places past the decimal here to make sure this is going to be accurate. Because remember, this is a percent. So for example, if you have 1%, that's 0.01 as a decimal. So you need to make sure you go far enough to actually see a decent amount of this decimal. So I'm going to go 4 places. So I'm going to say that my R is a negative 0.0462. Now think about the reason that your R value is negative. Okay, in this case, this is decreasing. It's actually exponential decay. Now you'll see some problems that you work out where it won't be decay and that R will be positive, and that's okay. It's just a matter of what it is that you're actually working with. So once we know R, we're just going to rewrite the equation, use the rate that we found, and solve for whatever the missing information is. So in this case, I'm trying to solve for when there will be 40% left. So my missing variable now is T. I know R, so I can go ahead and plug in E to the R, T. Then my initial amount and my starting amount, I don't know, but I know I need it to be 40% at the end. So I'll pick some easy numbers here. If I make this 100, then 40% of that would be 40. Okay, if you did 4 and 10, that would work. If you did 0.4 and 1, that would also work. But then follow the same process to isolate your variable. Divide by 100. Rewrite this as a natural log. And divide to get your answer. Now, if you haven't cleared out your calculator, you actually can get this pretty exact because you can use your previous answer to find your value. So I'll do the natural log of 40 over 100, and I'm going to divide that by the answer. So if you guys remember in your calculator, that's second and the negative, and that's your answer. So that gives me a time of 19.83, and that is in hours because I used hours in my original equation as my time. So whatever unit you started with, that has to be the unit for the second part as well. All right, so we're going to use that same process for most of these exponential growth and decay problems. Some of them may be a little bit simpler because it may actually give you the rate, but again, if you do not know the rate, if you only know some starting points or half-life, something along those lines, you need to make sure you actually solve for your rate first. The last one I want to look at is just a little bit of a different formula, and that's your compound interest formula. You probably saw this some last year. There's actually 2 different compound interest formulas depending on how often your interest is accruing. So the formula over there on the left, that's your compound interest for most cases. So the variables here, A is the amount after time, very similar to what it was. P is the principal, which is the starting amount. R is the rate, again as a decimal, always as a decimal. Now N, that's the new one. N is the number of times that the interest is compounded per year. Okay, the number of times the interest is compounded per year. And then T again is time. And we're going to do time in years for this. Okay, we're going to do time in years. Because we're doing the number of times it's compounded per year. We want those to be consistent. Now, if you're not quite sure what compounded means, that's basically how many times that interest keeps getting added back into your account. So for like a basic example, if I had $100 in an account, and I had 10% interest, then let's say that's compounded yearly. Well, then what that would mean is after 1 year, I would add 10% in, so then I would have $110. Well, then the next year, though, if I still have 10% interest, then the next year I'm actually getting that 10% of $110. So it's actually going to be more money the next year. The next year I'm going to make $11 and add that in. So I'm going to have $121 now. So the more often that interest gets added in, now let's say instead it gets added in quarterly. So if that interest gets added in quarterly, that first time, I'm still going to make in that year $10 of interest. But what's going to happen instead is after a quarter would be about 3 months. After 3 months, I would get that portion of the interest added in. So I would go ahead and get that extra $250, which means the next quarter I'm actually going to take that percentage of $102.50, and that's still in that quarter. So the more often your interest gets added in, the more money you're going to have. And with a small amount of money in a short period of time with a low percent, it's probably not going to make a large difference. But if you have a larger principal, more time, a higher rate, it actually can make a bit of a difference. Then the last formula we have, you probably saw last year in Algebra 2, that's your A equals PE to the RT. That is the exact same formula that we just did in the half-life question. It's just different variables. P stands for principal, but principal is your starting amount. A is the amount after time. That is the same thing as YT. So you don't need to learn a new equation here. Those are the exact same formulas. So the last one I want to work out is just an example of compound interest, so you guys can see, again, the difference between the two formulas. So it tells us $3,000 is invested in an account that pays 5% annual interest. How much more money would you make if the interest was compounded continuously for 10 years instead of compounded quarterly? So let's do continuously first. So that's going to be my A equals PE to the RT formula. So the amount after time I don't know, that's my variable. The principal is the starting amount, that's 3,000. E is E. My rate here is 0.05 because I have to write it as a decimal. And then times T, which is going to be 10. And what's nice about this is I don't have any algebra I really have to do to get my variable isolated. It's already by itself. So just make sure you get this typed in your calculator correctly. And after 10 years, you're going to have $4,946.16. Now let's compare that to if it was compounded quarterly. Okay, so if it's compounded quarterly, I need to use the other formula. I'm still looking for A. I still know 3,000 is a starting amount. Then it's 1 plus 0.05 divided by n, so the number of times it's compounded a year. If it's compounded quarterly, that's going to be 4. And then it's 4 times t. And I didn't mean to put n, I meant to put 4. And then my time here again is 10 years. And again here, your variable already by itself, so type this in your calculator and you should get your total value, which in this case is $4,930.86. So as you can see, you make more money the more often this is compounded. So if I subtract those two, I've got 49.46.16 minus 49.30.86, and that gives me a difference of $15.30. Alright, so we're going to look at a couple different examples of these growth and decay questions in class. So be ready to work on some more problems the next 2 days.